Hi, everyone. We'll start a new chapter today. Okay, this is chapter 10 in your textbook. Okay, today we'll begin to look at the structure and synthesis of alcohols. All right, in the opening photograph, these are some of the components. These are two of the components of peppermint oil. This is menthol and menthone. Menthone, of course, is a ketone, but it's the oxidation product of menthol. Alcohols are organic compounds that contain hydroxyl or OH groups. These are some of the most useful compounds in nature, industry, and around the house. And the reason for that is there are so many ways to make alcohols, and there are so many different functional groups that we can convert alcohols into. Right, in oxygen that occurs in water and alcohols, the oxygen is sp3 hybridized and therefore tetrahedral. This gives a bent geometry to the carbon oxygen hydrogen angle. Let me back up. The carbon that's bonded to the OH is referred to as the carbonyl carbon. Okay, it's important to be able to recognize classification of alcohols. Okay, first of all, we have methanol, where we just have a methyl group bonded to the OH. A primary alcohol is one with the OH bonded to a carbon, which is bonded directly to just one other carbon. For a secondary alcohol, the carbon with the OH is bonded directly to two other carbons. And a tertiary alcohol is one in which the carbon carrying the OH is bonded to three other carbons. Okay, these are all distinctly different from phenols, in which the OH is bonded directly to an aromatic ring or benzene ring. All right, so here we have examples of the four different classifications. This is a primary alcohol, okay, directly bonded to just one other carbon. Okay, it doesn't matter how many carbons we extend in this direction. It's still a primary alcohol. Okay, this would be a secondary alcohol. This is a tertiary alcohol. Okay, we use this compound in lab to make t-butyl chloride. And then this is a phenol. Right, to name alcohols, okay, Just like with any other functional groups, we find the longest carbon chain that contains the OH group. And then we drop the E from the alkane name and add all. Okay, so you can recognize alcohols because they'll end in all. Okay, even cholesterol, which we've been working with the last couple of weeks, that contains an alcohol functional group. Okay, we'll number the chain, giving the OH the lowest number possible. And then we'll number and name all substituents and write them in alphabetical order. Okay, so here are several examples of names. Okay, for primary alcohols, 2 carbons is ethane, so we drop the E. This becomes ethanol. Okay, we don't have to number the location for ethanol. This is 2-methyl-propan 1-ol. And this is what's called benzyl alcohol. Okay, that is distinct from phenol. Okay, notice the extra CH2 here. Benzyl alcohol reacts very differently from phenol. The secondary alcohol, okay, again, has 2 carbons directly bonded to the carbonyl carbon. Okay, so this is butan 2-ol. Okay, butane 4-carbon chain. The alcohol group is on number 2. Okay, if we have a cyclic alcohol, it's implied or understood that the OH is on carbon number 1. And so this is cyclohexanol. We don't have to say 1-cyclohexanol. And then here we have cholesterol. Okay, examples of tertiary alcohols. Okay, this is tert-butyl alcohol commonly. In the IUPAC, it's 2-methyl-propan 2-ol. Okay, both the methyl and the alcohol are on carbon number 2. Okay, this one would be triphenyl methanol. Okay, where the pH groups represent benzene rings. Right, this is 1-methylcyclopentanol. Okay, we don't have to locate the alcohol, but we do have to indicate where the methyl is located. Okay, here we have phenols. If phenol is the parent compound, the OH is automatically on carbon number 1. Phenol is a functional group, and it is the name of the simplest member of that functional group. Right, so this one becomes 3-methylphenol. This one is commonly called hydroquinone. Systematically, it would be benzene 1,4-diol. Okay, we'll talk about diols in a few minutes. Okay, if we have an alcohol and an alkene, the alcohol group takes precedence. Okay, there's a new method of nomenclature that was adopted around 1997, in which the locant is positioned right before the infix, the ene infix. Okay, so the newer method would say pent 4-ene 2-ol. Okay, so this is an overview of the priorities of functional groups. Okay, several of these we haven't covered yet. Okay, halides are the lowest. Also nitro groups, NO2 groups are way down at the bottom. Any alkyl substituents would be at the bottom. Then we have ethers, and then alkenes and alkynes. then above alkenes and alkynes, we have amines, then alcohols, then ketones, aldehydes, esters, and then above everything else, way up at the top, are the carboxylic acids. Okay, so carboxylic acid takes precedence over an alcohol. Okay, so the alcohol is a primary functional group. Okay, the alcohol is automatic. The carboxylic acid is automatically on carbon number 1. Butane is 4, so this is butanoic acid. And the alcohol group as a substituent is a hydroxy. Okay, this is also known as gamma hydroxybutyric acid. That's a common name. Many alcohols are known commercially by their common names. We saw this one just a few minutes ago, 2-methyl-propan-1-ol, commonly called isobutyl alcohol. And butan-2-ol is sec-butyl alcohol in the common nomenclature. Okay, if we have 2 alcohols, both of those need numbers, and the prefix for 2 is di. So a diol is a compound that has 2 alcohols. Right, so this is hexane 1,6-diol. Okay, we retain the E because the next letter is a consonant. 1,2-diols are commonly called glycols or vicinal diols. And this one right here on the left, in the IUPAC, it's ethane 1,2-diol, and its common name is ethylene glycol. Okay, you remember that ethylene was a compound with a carbon-carbon double bond. Okay, but you can see there's no double bond. Okay, that is because this was made from ethylene. This is the glycol that was made from ethylene. Right, and then this is propane 1,2-diol or propylene glycol. Right, both of these compounds are used as antifreeze and coolant in car radiators. Okay, they have 3 properties that suit them to this purpose. Okay, because of the 2 alcohol groups, you have a lot of places for hydrogen bonding, so that means a high boiling point. Okay, whereas water boils at 100 degrees Celsius, ethylene glycol boils at about 189 Celsius. Also because of the 2 OH groups and the ability to hydrogen bond, ethylene glycol is infinitely soluble in water. And in fact, antifreeze coolant that you use in a car radiator is not straight ethylene glycol, but instead it's a mixture of ethylene glycol and water. Okay, there'll be some other components like the dye and the corrosion inhibitors. Okay, propylene glycol likewise is more recently used in car radiators. Ethylene glycol is this is the main ingredient in the antifreeze that's dyed green, and then propylene glycol is the one that's dyed orange. Okay, phenol nomenclature. The OH is assumed to be on carbon number 1, okay, as long as the phenol is the dominant functional group. For common names of di-substituted phenols, ortho represents 1, 2, meta is 1, 3, and para is 1, 4. And methylphenols are commonly called cresols. Okay, so in the IUPAC, this is 3-chlorophenol. Okay, I'm just going to ask IUPAC, but just you may come across these common names. Okay, and it's metachlorophenol. Okay, meta means it's 1,3 disubstituted. Okay, this is 4-methylphenol or paracresol. Okay, so name this compound. Right, the longest chain that contains the OH would be this one right here, 1, 2, 3, 4, 5. Okay, the longest chain in the compound is 6. Okay, but we want to use this chain right here because it contains the dominant functional group. Okay, so the main chain here is 5. And substituents, this would be an iodomethyl. This would be an isopropyl. Okay, so the correct name for this compound is 3, and then in parentheses, iodomethyl. Okay, that's a substituent on a substituent. And 2 isopropyl pentan 1-ol. Okay, what about physical properties of alcohols? Alcohols have high boiling points due to their hydrogen bonding between molecules. They have higher boiling points than many other functional groups except carboxylic acids. Small alcohols are miscible in water, but solubility decreases as the size of the alkyl group increases. All right, so methyl alcohol is known as methanol in the IUPAC, CH3OH. Its boiling point is 65, and you can see that these alcohols are typically less dense than water until we get to the ones that have the benzene rings on them. Okay, so boiling point goes up as the number of carbon atoms increases. Okay, here at the bottom we have propane 1,2,3-triol, commonly known as glycerol. It has 3 alcohol groups and its boiling point is 290. Okay, so here we have ethanol. Ethanol has the same molecular formula and molecular weight as dimethyl ether. It has a similar molecular weight to propane, okay, 46 versus 44. And notice the difference in boiling points. Ethanol boils at 78. Dimethyl ether boils at -25. Okay. Dimethyl ether can only accept hydrogen bonds, it cannot donate. So there's no intermolecular hydrogen bonding with dimethyl ether. In the case of propane, you only have London dispersion forces. So here, boiling point is much lower, -42. Okay, so this illustrates the hydrogen bonding that takes place in ethanol. Hydrogen is strongly attracted to the lone pair on the oxygen of a nearby molecule, whereas with dimethyl ether or ethers in general, you don't have this intermolecular hydrogen bonding. Okay, let's look at solubility in water next. Right. Methanol, ethanol, propane, 1-ol, tributyl alcohol are all miscible in water. We get to isobutyl alcohol, and solubility drops to 10%. And as the size of the R group increases, solubility goes down. Okay, so N-hexyl or 1-hexanol, hexane 1-ol, is only about 0.6% soluble in water. By the time we get to 10 carbons, we've got an alcohol which is completely insoluble in water. Okay, whereas N-hexyl alcohol is 0.6% soluble, hexane 1,6-diol is miscible. Right, let's look at some commercially important alcohols. Methanol is commonly called wood alcohol. It was first isolated actually in the late 1600s by the distillation of wood in the absence of air. That's where it gets its name. It is important in the industrial production of synthesis gas, synthetic fuel. It's a common industrial solvent. Okay, it's miscible in water, and it also dissolves a number of organic compounds very well. The toxic dose is about 100 milliliters. Consuming methanol instead of ethanol it can be fatal. If a person doesn't consume enough to cause death, it can also cause severe digestive problems, and also it can cause blindness. Okay, you may have heard in the news that there have been some hand sanitizers, especially hand sanitizers that have been imported, that contain methanol, and these are dangerous to use. Methanol can be absorbed through the skin. Okay, methanol is also used as a fuel. It is the fuel that they use in the Indianapolis 500 cars. Also, drag racing cars use methanol, and the methanol may be combined with nitromethane. Okay, if there's a car crash and a fire, the fire can be extinguished with water as opposed to a gasoline fire. Methanol does have a high octane rating. It's about 105. It burns cleanly, it has low emissions, but it does have a low energy content per mole, and it burns with a nearly invisible flame. Ethanol can be produced in a couple of different ways. One that's mentioned here is fermentation of sugar and starches. It can also be produced from ethylene that's obtained from natural gas and petroleum. Okay, so when sugar or starches are fermented using yeast, ethanol is one of the products. Once the fermentation achieves about 12 to 15% ethyl alcohol, the yeast cells will die, and then there's no more increase in the alcohol content. So Wines, for example, will contain approximately this amount, this percentage of alcohol. Other alcoholic beverages, which contain higher percentages, require distillation. Okay, things like vodka, bourbon, whiskey, and many others. When ethanol is distilled, you get what is called an azeotrope. And what this is, it's a constant boiling mixture. It behaves like it's a pure compound. Okay, if you do a distillation graph, you get a clean separation between two liquids. Okay, your temperature versus volume graph looks something like this. Okay, this is the lower boiling compound. As long as we're just boiling that off, we get a level curve. And then up here, we've distilled this all the way, and then we've got just the second component, and then we've got a level curve here. Now with an azeotrope, we'll get a level curve, and it's not a pure compound. Okay, it turns out that 95% ethanol, 5% water, actually has a lower boiling point than 100% ethanol. And so if ethanol contains any water, okay, it is not possible to completely separate it just by distillation. Okay, since this mixture always has a lower boiling point. Several years ago, there were some ethanol plants that actually went out of business because they didn't understand this. They thought that if they built taller fractioning columns and more furnaces and so on, they could achieve a higher percentage of ethanol. Ethanol that is to be used for fuel, okay, especially if it's going to be mixed with gasoline to form gasohol, it needs to be a higher percentage than this. Okay, and so what is done is to add benzene to the ethanol water mixture, and then you get a 3-component azeotrope that boils off that contains the benzene, most of the water, and a little bit of ethanol. The resulting material in the distillation container contains a little bit of benzene, so it's unsuitable for beverage, but it can be used as a fuel. Right, denatured alcohol is ethyl alcohol that has been deliberately made poisonous, and it's used as a fuel or a solvent. The reason for that is that because of the use of ethanol in alcoholic beverages are very highly taxed. As much as 80% of the cost of alcoholic beverages is actually tax. And if you're going to be using alcohol for some other purpose and not have to pay the tax, you can denature the alcohol, and a common denaturant is methanol. Methanol and ethanol are very, very difficult to separate from each other. Gasohol is a mixture of 10% ethanol in gasoline. Okay, the toxic dose of ethanol is about 200 milliliters. I want to mention one other term here. That is proof. Right, proof is 2 times the percent ethanol by volume. Okay, in many alcoholic beverages and even lab alcohol is labeled with proof. 100% ethyl alcohol, also called absolute alcohol, is 200 proof. Okay, so whiskey is often something like 86 proof, which means it's 43% ethanol by volume. Okay, I'm not sure where the factor of 2 comes in, but the origin of the term actually goes back over 200 years. In the late 1700s in Great Britain, whiskey merchants would water down their product. And this was to increase their profits. And one way to test whiskey to see whether it had been diluted was to mix it with gunpowder and see if the gunpowder would ignite. If it had been watered down, then the gunpowder wouldn't ignite. Right, propan 2-ol, commonly called isopropyl alcohol, is made industrially from propylene by the catalytic addition of water. And isopropyl alcohol is commonly used as rubbing alcohol. And it comes in various percentages. I've seen 50%, 60%, 70%, 91%. Okay, and it really has to be at least 60% isopropyl alcohol to be effective as an antiseptic. Right, let's consider next the acidity of alcohols. Okay, water has a pKa of 15.7. Alcohols have a similar pKa range. Most alcohols, though, are a little bit less acidic than water. Acidity decreases as substitution on the alkyl group increases. Halogens and other electron withdrawing groups that are nearby will increase the acidity. Phenol is 100 million times more acidic than cyclohexanol. Okay, that's one of the reasons why phenols are classified in a separate functional group. Okay, so here we have some representative pKa values. Okay, methanol and ethanol are pretty similar to water. Okay, if we have a chlorine on position number 2, 2-chloroethanol, the chlorine is electron withdrawing. That will stabilize the negative charge on the conjugate base. And so that increases the acidity by more than 10-fold. Okay, if we have 3 chlorines on the 2 position, okay, that has a much more significant effect on the acidity. Okay, here it's more than 1,000 times. Okay, 3 pKa units, 1,000. Okay, on the previous slide, I talked about the degree of substitution. So isopropyl alcohol is less acidic than propyl, than ethanol. Tert-butyl alcohol is even less acidic. Okay, so this is 100 times less acidic than ethanol. Cyclohexanol is about 18, and then phenol is 10. Okay, and then just for comparison, again, water's 15.7. Acetic acid, okay, carboxylic acids, of course, are known for their acidity, 4.74. Okay, so more than 10 pKa units less than most of these alcohols, and hydrochloric acid is -7. Okay, generally doesn't work very well to produce an alkoxide ion with hydroxide, because you're trying to go from a stronger acid to a weaker one. Okay, this is actually an oxidation reduction reaction. One common way of producing alkoxide ions is to use an active metal like sodium or potassium. Okay, so what happens here with ethanol is, okay, sodium metal, it's a pure element that has no charge. And so it loses an electron, so it gets oxidized. Okay, oxidation is loss, reduction is gain. Remember oil rig. Okay, and then the element that gets reduced is hydrogen. Okay, hydrogen is +1. Its oxidation number is +1. And in hydrogen gas, it's 0. Okay, so hydrogen is gaining, sodium is losing. And the stoichiometry here is we have 2 to, it's actually, 1 to 1. Okay, more hindered alcohols like 2-propanol and tert-butyl alcohol. We typically use potassium. Potassium is more reactive than sodium. Okay, if you're starting with a phenol, okay, hydroxide won't work very well in forming the conjugate base of cyclohexanol, but with phenol, okay, this goes to completion. Okay, we have a stronger acid, pKa 10, forming a weaker acid, 15.7, water, and so this works. Okay, so why is phenol so much more acidic than cyclohexanol? We can answer that in one word, and that's resonance. Okay, with cyclohexanol, okay, once we lose that proton, the negative charge on the oxygen will not go anywhere and can't be delocalized. But here, with phenol, you can see that we can spread that negative charge all the way around the ring. So we have 4 resonance structures. Resonance delocalization is a highly stabilizing phenomenon. Okay, we'll probably just get started on this. Okay, there are many ways to synthesize alcohols, and some of these we've already seen. We'll introduce some new methods as well. Okay, they can be synthesized by nucleophilic substitution. Okay, usually SN2 of an alkyl halide. So if we have something like 1-bromobutane, we can react this with hydroxide. Hydroxide comes in from the back side, kicks out the bromine, and our product would be butan-1-ol. Mentioned here, don't draw a bromine leaving like this. Okay, we need to represent this bond breaking. You guys saw a few examples of that on the test. Okay, we form this bond, and at the same time we break this bond. Okay, we can also add water to double bonds. Okay, so this is pent-1-ene. Acid catalyst and water. Okay, this would follow Markovnikov's rule. And so our product would be pentan-2-ol. Okay, using mercury 2-acetate and water followed by NaBH4. Okay, we get the same thing. We get hydroboration oxidation using borane THF, followed by hydrogen peroxide, H2O2 and OH minus.
Dr. Trump, could you move the camera up a little bit?
Oh,
Please.
okay, sorry. Yeah.
Good.
Oops, wrong way. There we go. Okay, this would give us the anti-Markovnikov. So we would get pentan-1-ol. All right, so these are some of the methods that we've already seen for preparing alcohols. In the chapter on alkenes, we also saw methods of producing vicinal diols. Okay, using osmium tetroxide and H2O2. We can produce a cis diol. Okay, we could also use cold dilute KMNO4 solution. All right, both of these would produce a cis diol. Right. Right, to make a transdiol, this requires 2 steps. Right, first we would make the epoxide. Okay, so using something like MCPVA. Right, this is MCPVA. Okay, we would first make the epoxide, and Chapter 8 specifically mentioned acid catalyzed ring opening. So using dilute acid and water, we can open this up. And this gives us the transdiol. Okay, the steps that occur, first oxygen on the epoxide gets protonated, water attacks, and it has to attack from the backside. And it attacks from the backside, that breaks this bond, opens up the ring. We get the transdiol, plus we also get the enantiomer. Okay, that would happen if water attacked the other side. Okay, so we can do either syn hydroxylation or anti-hydroxylation. All right, I'm going to go ahead and stop here. And this represents some new methods for synthesizing alcohols.